NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve floor function equations using the definition. We will follow a precise 3-step algorithm and apply it to an example. We will now walk through a complete example, step by step. Solve the equation, floor of 2x minus 1 equals 4. We begin with the definition. If the floor of f of x equals n, then n is less than or equal to f of x, and f of x is less than n plus 1. Step 1. Identify the integer n. Here, the right side is 4, which is an integer, so n equals 4. Step 2. Apply the definition. Replace the floor with a double inequality using n equals 4. That gives 4 less than or equal to 2x minus 1, and 2x minus 1 is less than 5. Step 3. Solve the double inequality for x. First, add 1 to all 3 parts. Then, divide everything by 2 to isolate x. Let us visualize the solution on a number line. A closed point at 2.5 and an open point at 3, with the interval shaded in between. Therefore, the solution set is all x in the interval from 2.5, inclusive, up to 3, exclusive. Here is the problem. We need to solve left floor of open parenthesis 3x plus 1 over 2 close parenthesis right floor equals 4 times open parenthesis 4 minus x close parenthesis over 3. To handle the floor, we use a key property. For any real y minus 1 is less than the floor of y, and the floor of y is less than or equal to y. We will substitute y equals open parenthesis 3x plus 1 close parenthesis over 2. Since the floor of y equals 4 times open parenthesis 4 minus x close parenthesis over 3, we can place it between y minus 1 and y, producing a pair of inequalities that x must satisfy. Let's solve the left inequality. 3x plus 1 over 2 minus 1 is less than 16 minus 4x over 3. Clearing denominators gives 9x minus 3 is less than 32 minus 8x. Adding 8x to both sides and adding 3 to the right yields 17x is less than 35. So x is less than 35 over 17. Now, the right inequality, 16 minus 4x over 3 is less than or equal to 3x plus 1 over 2. Clearing denominators gives 32 minus 8x is less than or equal to 9x plus 3. Move terms to get 29 is less than or equal to 17x. Therefore, x is greater than or equal to 29 over 17. Combining both, x must lie between 29 over 17 inclusive and 35 over 17 exclusive. Let's picture that on a number line, and also mark the candidate x value 7 over 4 in the middle for later. Now set y equals open parenthesis 3x plus 1 close parenthesis over 2. Pushing the entire x interval through this linear expression gives a y interval from approximately 3.058 up to about 3.588. Since all such y values lie strictly between 3 and 4, the floor of y is always 3 on this interval. Because the floor of y equals an integer, the right-hand side, 4 times open parenthesis 4 minus x close parenthesis over 3, must also be that same integer on the allowed x range. We just found the floor is 3, so set the right-hand side equal to 3 and solve for x. Now we verify that 7 over 4 lies inside the interval 29 over 17 to 35 over 17, and we check it in the original equation. Plugging in 3x plus 1 over 2 equals 3.125, floor is 3, and the right side equals 3, so it matches. Therefore, x equals 7 over 4 is a valid solution. Conclusion. The solution set consists of a single number. X equals 7 over 4. Example. We will solve the equation with the floor function exactly following a clean, step-by-step algorithm. The bracket denotes the floor function. Step 1. Isolate the floor term. Move it to the other side. Important domain note. Because x squared is in the denominator, we must have x not equal to 0. Step 2. Divide both sides by 2x. This gives us a simpler comparison. Step 3. Simplify both sides. On the left, split the fraction. On the right, split the fraction. On the right, split the floor argument. For the floor function, floor of 1 plus it equals 1 plus floor of a. Now, subtract 1 from both sides. Step 4. Introduce a new variable. Let 3y over 2x equal k. Because the right side is an integer, 1 plus k is an integer, so k must be an integer. Substitute y over x equals 2k over 3 into the right side. Step 5. Convert the floor equation to a double inequality. 1 plus k is less than or equal to 4k squared over 9, and strictly less than 2 plus k. This gives two quadratic inequalities. Solve the first. It leads to k less than or equal to negative 0.75, or k greater than or equal to 3. Solve the second. It gives k strictly between approximately negative 1.28 and 3.53. Intersect the two ranges. Step 6. Since k must be an integer, the only integer values inside these intervals are k equals negative 1 and k equals 3. Here is a quick number line to visualize the allowed k values. Step 7. Back substitute. If k equals negative 1, then 3y equals negative 2x, so y equals negative 2/3 x. If k equals 3, then 3y equals 6x, so y equals 2x. Remember the domain x is any real not equal to 0. Final answer. The solution set consists of two linear relations, y equals negative 2/3 x, or y equals 2x with x non-zero. Example. We will solve the equation with floors. Floor of open paren x minus 2 over 2 close paren minus open paren x minus 2 close paren equals x over 2 minus floor of open paren 2x minus 1 over 4 close paren. Step 1. Use the floor definition. For any real a equals floor of a plus p, with p in the interval from 0 inclusive to 1 exclusive. Apply that to both floor terms and introduce p sub 1 and p sub 2. We also visualize that each p lies in the half-open interval from 0 to 1. Step 2. Substitute the floor expressions into the equation and simplify carefully. Collect like terms to isolate p sub 1 plus p sub 2, then clear denominators by multiplying by 4. We obtain negative 2x plus 3 equals 4 times the sum of p sub 1 and p sub 2. Step 3. Since each p is between 0 inclusive and 1 exclusive, their sum satisfies 0 less than or equal to p sub 1 plus p sub 2 less than 2. Multiplying by 4 gives 0 less than or equal to 4 times the sum less than 8. Because negative 2x plus 3 equals that quantity, we have the double inequality. 0 less than or equal to negative 2x plus 3 less than 8. Step 4. Subtract 3 throughout to get negative 3 less than or equal to negative 2x less than 5. Divide by negative 2, remembering to flip inequality signs. We obtain negative 5 halves is less than x, less than or equal to 3 halves. Step 5. We test values inside this interval. Try x equals 0. Compute both sides to confirm equality. Now test x equals 1. Show that the two sides are not equal. Test x equals negative 1. Again, not equal. Therefore, only x equals 0 satisfies the original equation. Final result. Only x equals 0 works, so the solution set is curly brace 0. Example. Here is the problem. Floor of x plus 1/2 plus the square of floor of x equals floor of 2x plus 2. We'll use bracket notation for the floor function. A quick note. In this lesson, square brackets represent the floor function. Step 1. Use Hermite's identity. For any real x, floor of 2x equals floor of x plus floor of x plus 1/2. Now isolate floor of x plus 1/2. It equals floor of 2x minus floor of x. Step 2. Substitute and simplify. Start from the original equation. Use the integer shift property. Floor of a number plus an integer, n equals floor of the number plus n. Since 2 is an integer, floor of 2x plus 2 equals floor of 2x plus 2. Now substitute Hermite's result for floor of x plus 1/2. Then subtract floor of 2x from both sides to simplify. Step 3. Rearrange into a standard quadratic equation in the unknown floor of x. Factor the quadratic. Let y equal floor of x. Then y squared minus y minus 2 equals 0, which factors as y minus 2 times y plus 1 equals 0. Therefore, floor of x equals negative 1, or floor of x equals 2. Step 4. Translate these to x intervals using the definition of the floor function. If floor of x equals n, that means n is less than or equal to x, and x is less than n plus 1. For floor of x equals -1. X is between -1 inclusive and 0 exclusive. For floor of x equals 2, x is between 2 inclusive and 3 exclusive. Let's visualize both on a number line. Therefore, the complete solution set is the union of two intervals, -1 to 0, including -1, but not -1, but not including 0, and 2 to 3, including 2 but not including 3. Recap. We used Hermite's identity to replace floor of x plus 1/2 with floor of 2x minus floor of x, applied the integer shift property to floor of 2x plus 2, reduced the problem to a quadratic in floor of x, solved for floor of x, and translated those values to x intervals using the floor definition. Reduced the problem to a quadratic in floor of x, solved for floor of x, and translated those values to x intervals using the floor definition. We will follow a clean strategy using the integer and fractional parts of x. Step 1. Write x as n plus p, where n is an integer and p is in the interval 0 to 1. So x equals n plus p, with 0 less than or equal to p and p less than 1. Substitute this into the original equation. Because n is an integer, it can be pulled outside the floor. After canceling the two n terms on both sides, we get the key reduced equation in p, open bracket p minus 1/2 close bracket plus open bracket p plus 1/2 close bracket equals open bracket 2p close bracket. Now we analyze by cases on the fractional part p. We will visualize p on the unit interval from 0 to 1, focusing on the midpoint 1/2. Case 1, p between 0, inclusive, and 1/2, exclusive. Here p minus 1/2 lies between -1/2 and 0, so its floor equals -1. Also p plus 1/2 lies between 1/2 and 1, so its floor equals 0. And 2p is in 0 to 1, so the floor of 2p is 0. Equation left side becomes -1 plus 0, while the right side is 0. That is -1 equals 0, a contradiction. So there are no solutions in this interval. Case 2, p between 1/2 inclusive and 1 exclusive. Now p minus 1/2 is between 0 and 1/2, so its floor is 0. Also p plus 1/2 is between 1 and 3/2, so its floor is 1. And 2p is between 1 and 2, so the floor of 2p is 1. Then the left side is 0 plus 1, and the right side is 1. That is 1 equals 1, which is true. Therefore, every p in this interval works. Finally, we translate the condition on p back to x. Since p is between 1/2 and 1, we have n plus 1/2 less than or equal to n plus p, which is x, and x is less than n plus 1. Equivalently, x is in the interval left bracket 2 n plus 1 over 2, comma, n plus 1 right parenthesis. Taking the union over all integers, n gives the complete solution set. Let's also visualize several of these intervals on the real line. Here is our problem. 3 times bracket x plus 1 bracket plus bracket -x plus 1 bracket equals bracket x plus 2 bracket. Step 1. We use the shift by integer rule. The floor of x plus k equals the floor of x plus k, when k is an integer. Applying this, 3 bracket x plus 1 bracket becomes 3 times bracket x bracket plus 3. Bracket -x plus 1 bracket becomes bracket -x bracket plus 1. And bracket x plus 2 bracket becomes bracket x bracket plus 2. Now expand and combine like terms. Move all terms to one side to isolate 0. Finally, subtract 2 from both sides to simplify. Step 2. We use the symmetry identity for the floor of -x. If x is an integer, the floor of -x equals negative the floor of x. If x is not an integer, the floor of -x equals negative the floor of x minus 1. Now we split into two cases, integer x and non-integer x. Case 1, x is an integer. Substitute to get 2x plus -x equals -2. So x equals -2. That is a valid solution. Case 2, x is not an integer. Substitute the second formula. We get 2 floor of x plus negative floor of x minus 1 equals -2. So floor of x minus 1 equals -2. Therefore, floor of x equals -1. The floor of x equals -1 means x is between -1 and 0, including -1, but strictly less than 0. But because our case assumes x is not an integer, we exclude -1 and keep the open interval from -1 to 0. Let's visualize the solutions on a number line. We will show the open interval from -1 to 0 and the separate point -2. First, highlight the open interval from -1 to 0. Open at -1 and open at 0. Next, mark the single point at -2 with a filled dot. Finally, we combine both parts. The solution set is the open interval from -1 to 0, together with the single point -2. As a quick check, pick a number like -0.3. Its floor is -1, and the equation balances. 4x equals -2, substitute directly, and you can confirm the equality holds. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.